Good morning and welcome to the AMA Expo stage presented by Nationwide Insurance. Air launch to orbit, flight testing the towed glider, the twin boom glider that was here last year has been tested and flown. And Jerry Budd and Red Jensen have a great presentation for you with accompanying video to show you how successful this program was. Please give a warm AMA welcome to Jerry Budd.
It's really nice to be here. Some of you may remember, if you were here 2 years ago, I gave a presentation on this concept that we were just getting started. We had on display the same glider, but it was a mock-up, and that the center wing was not the flight article, and we hadn't flown it. The vehicle that we've got over there, if you get a chance, go talk to Derek and Red, and they can kind of step you through the tour of the vehicle and the van that we fly it out of. This is an update to that briefing. A lot has happened in 2 years. Like most people's lives, projects move along, things happen. We were able to get approval as a formal NASA project in September 4th with this through the Space Technology Mission Directorate with $250,000 funding and about 10 FTE of government labor and instructions to come back with an external commercial government partner to turn this into an X-plane, along with flight testing, the model that you see over there. So I'm going to give you a quick update on that. I'm going to step right into a little bit about why. Because we shouldn't be doing anything unless there's a good reason why. And essentially what this is about is launch-on-demand access to space. A lot of people will coin it a different way, where it's cheaper, more efficient access to space, commercial access to space instead of government-sponsored launches and so forth. But really, you've got to cut down the time, advanced planning and approval time, because what happens is right now a manifest process to put something to orbit is about 3 years. And that is just way too long. For the big, large 3 million pound rockets, the Delta IV Heavies, things like that, I can kind of see that. The satellites are, more expensive than probably this building times 10. But for this, everything's going smaller. Electronics go smaller. You see it in the hobby industry. The satellites are getting smaller. Electronics are getting cheaper, and they need more agile access to space. So the target that we're shooting for is basically 100 pounds to orbit for $1 million launch, and we're working with the FAA to get the approval time from basically 3 years down to 6 months, down to maybe 6 weeks, maybe down to 6 days. So we're pretty aggressive about that, and the reason why is if you're a launch provider and you're going through that process, you've got a standing army of wages that you're paying, and pretty soon you get to the point to where the labor costs more than the hardware, and that's not a good thing when you're trying to be agile and keep costs low. So to get to agile and launch on demand, there's basically 3 things that have to happen. A lot of work people call this plug and play, but essentially you need on-the-shelf satellites that are ready to be deployed. You're not building it, it's sitting there ready to go depending on what you're wanting to do. You've got rockets or launch vehicles sitting on the shelf ready to be plugged together and integrated with that, and you need a launch platform that gives you quick turnaround times. So what we're proposing is that these elements are very close to being realizable, but we kind of got to get it over the tipping point. And so we came up with the concept of a towed glider, which is the first aspect of this, as a different way to approach launching things to orbit. Now, air launch has been done before. Orbital Sciences has got around 50 launches on the Pegasus. But the smallest launch vehicle that you can buy today, anywhere, is a Pegasus that launches a little under 1,000 pounds to orbit for a little over $50 million. And you're looking at that 2 to 3 year approval process to get manifested, even though it's an air launch. And part of that is because of the approval cycle. Part of it is because of the size. And so we're looking for something a lot more agile, a lot more flexible. Secondly, you really want to have more than one launch vehicle available. And the reason for that is competition. Anytime you only have one source for something, the cost never goes down with time, it goes up. Yet with time, technology, costs should be going down. It's because you don't have competition. So what we're advocating is multiple launch vehicle companies providing rockets to be launched off the glider. And then the third thing that we're doing is we're working with the FAA on this behind-the-scenes policy to essentially make tailored launch processes for approval. You still have to meet the same safety requirements when you launch air launch, and even if there's this perception if you take something 100 miles out over the ocean that you don't have to meet any of those requirements, no, you do. If you launch anywhere in the world and you're a U.S. entity, you have to meet the same safety requirements. It doesn't matter what population, whether it's our country or some other country. But what happens is when you get 30, 50, 70 miles, 100 out over the ocean, there's not very many people around. It becomes a lot easier to meet those requirements, and you have a lot more flexibility on your schedule. Your launch coordinates can be moved around to avoid delays due to weather, et cetera, et cetera. So essentially what we're proposing is something that we hope will ignite the small launch market and make operationally responsive space a reality. So what I'm going to do here is we've got an animation that I'm going to show you that NASA Langley put together for us. But basically what we're talking about is a 3-year project to build roughly a 100-foot wingspan glider carrying approximately a 6,000-pound launch vehicle to altitude, meaning 40,000 feet, carrying a satellite of about 100 pounds that you would ultimately put to orbit. And what's different about this is as compared to a Pegasus launch, is we're not going to launch in level flight, and you'll see it in the animation. So what this shows is a G3 sitting on the runway with about a 1,000-foot long tow line to a swept wing glider. Now the glider we have on display is straight wing, but you really want to sweep the wings on the glider to match the tow plane, because there's not a lot of straight wing tow planes available that go to 40,000 feet. And the advantage of that is it lets you fly at a little bit higher speed, but mostly match up the flight envelopes as you do the tow and the climb to 40,000 feet. At 40,000 feet leveled off, you would release the tow line from the glider, which will be shown here in just a moment. There it is. And then you will clear the area of the tow plane so that it's not in the road. And what we have is a small throttleable, restartable rocket motor on the glider itself that will ignite and propel the glider with the rocket under it up through a pull-up to about a 70-degree angle at constant airspeed, at which point the rocket motor on the motor on the launch vehicle will ignite after it releases, which is happening right there. And then the glider simply pulls on over and does a chandelle or an Immelmann to head back from where you launched it from, and the rocket continues onto orbit. And the advantages of air launching this way, there's a bunch of them, I've got it on a chart, but the primary advantage is that you get a big bump in performance, like maybe double compared to what you get from ground launching a rocket. And there's a variety of safety advantages and other things. So essentially what we're doing is we are giving the rocket a head start, not only in terms of altitude, but also in terms of the flight path angle, because if you launch it in level flight, you've got to turn the corner to where you're pointed much more upward instead of at the horizon. And when you do that, you burn a lot of energy. By turning the corner with the wing and using a rocket motor that's on the glider, not on the rocket, you keep all the propellant on the rocket for the ascent, which means a smaller, cheaper, less expensive, simpler, more reliable system. So we wind up with 2 rocket systems. The one on the glider, we're calling it a sustainer motor, and you can see all the merits of that is throttleable, restartable. The other advantage of a restartable motor is that once we release the rocket and we're gliding back, if we're far enough offshore that we can't reach shoreline, you can restart the motor, pull up hard, gain 30,000 feet, level off and glide for another hour, another 200 miles. So one of the questions is, well, why tow glider? Why not direct carry if you're going to air launch? Our friends up in Mojave at Scaled Composites are building an airplane for stratolaunch, which is going to be the largest airplane in the world, 385-foot wingspan, carry a 500,000-pound rocket. They had to build the world's single opening door hangar, a 400-foot door to actually build and house the airplane in. The rocket's 500,000 pounds. It'll be 1.3 million pound takeoff, 6 747 engines, 3 sets of landing gear, et cetera, et cetera. Well, there's obviously an advantage to air launch, otherwise Paul Allen wouldn't be spending that much money. It turns out that if you tow a glider behind an airplane instead of carry the rocket directly under the airplane, you can carry 2.5 times more weight than you can direct carry. And a way to look at that is people who fly sailplanes full scale, typically a glider tow, a Super Cub, or tow plane. The sailplane is going to weigh 1,500 pounds with the 2-seater and with water ballast, maybe as much as 1,800. The tow plane can't deadlift that. It'd never get off the ground, but it can easily tow it. There's 2 reasons why It's aero efficiency of the glider, the lift to drag ratio, and it's also the structural ability of the glider to carry that weight. And the reason that is because the glider it's like a model airplane. It's an aeroshell. There's nothing to it. It doesn't have fuel systems. It doesn't have avionics. It doesn't have plumbing. It doesn't have hydraulics. It doesn't have engines. It doesn't have fuel tanks. You don't have any of that. And with the glider being remotely piloted, you also don't have a crew. You don't have egress, oxygen systems, life support, ejection seats. All of that weighs. So every pound that you're not carrying in terms of crew and life support and engines is another pound of rocket that you can lift. And so that is a big advantage. The other part of it is that this pull-up maneuver that we're talking about gives you another 12 to 15% performance advantage over a horizontal launch at altitude. It totals up to almost double. And you're not going to be able to do that maneuver with a crewed aircraft. Now, the exception to that is the ASAT program that the Air Force did back in the mid-80s was air launch off of an F-15. The problem with that is that you're growth limited. You can't get any bigger. This is a scalable concept. If you need to carry, instead of a 6,000-pound rocket, you want to put 200 pounds to orbit, you carry a 12,000-pound rocket, and you make the glider about 20% bigger. So you can size it to whatever you want. An F-15, you will never put 12,000 pounds under centerline on that. There's lots of other advantages. There's a safety advantage in the fact that right now, anything you carry in a rocket system on a manned or a piloted airplane, you have to human rate the rocket system, which costs money and take time. Since the glider has nobody on board, I don't have to human rate the rocket or the glider, which again translates into money, cost, et cetera, et cetera. And then there's lots of flexibility issues of being able to take the glider apart, put it in a transport, take it somewhere else in the world, more of a military application. But basically, the tow glider concept is really the optimization of air launch. I'm going to talk just very briefly about carry efficiency. These airplanes here, the B-52 and the L-1011, carry payloads external. And that's basically what we could have carried off the B-52 that we had at NASA for 50 years. And this is the weight of the Pegasus Max on the L-1011. It can carry a little bit more internal, but externally that's all you can do. And it gives you a weight fraction, which is basically the weight of what you're lifting divided by the weight of the system minus what you're lifting. And that is about as good as you're going to get. Dedicated carry airplanes like White Knight 2 are up around 71%. The target numbers we're shooting for is 1.5 to 2. Nothing's ever flown. Yet, if you again think about your sailplanes at the glider port, they routinely do that. So while those are staggering numbers, it's actually nothing that hasn't already been done. This is really a systems integration problem. So what does that mean? This is a chart, excess thrust required by the tow plane as a function of carry efficiency and glider max L over D. Okay, what it really means is this is how much thrust do you have to have per pound of mass that you're carrying to altitude. So lower is better. This is the carry efficiency. It's that structural ratio I was talking about. To the right is goodness. And basically, as the structural efficiency goes up, that weight or the extra thrust goes down. As the L over D goes up, the curves shift down. So both of those combined is what we're leveraging in doing this. And to put it in layman's terms, everybody remember when they took Endeavour and took it from LAX to downtown to put it in the museum and they're towing it with the Toyota truck and all that? Well, certainly you would never carry that on a Toyota truck, but you can tow it. So that's kind of a way to look at it, and it's pretty much the same thing. It's how you basically weight distribution is what you're talking about. The other thing about the glider design, I touched on this earlier, is the trade space aspect. This is basically current state of the art for direct carry. And the problem is it's a real estate problem, putting something underneath an airplane. Putting something on top is really a safety issue. You can't get rid of it in an in-flight emergency. You've got separation analysis because it's a manned aircraft. You know, you've got the size is limited by the base aircraft. The maintenance costs on some of the high-performance airplanes are fairly high. And what we are postulating is that by going to a towed glider next generation approach, most, if not all, those constraints go away. And the glider will be cheaper to build because, again, it's an empty airplane. It's an aeroshell with just some avionics. We had a study done by Burt Rutan and a couple other folks back in 3 years ago. All three of the people, it was Burt Rutan, Ray Morgan, who was the Vice President of Environment, the Helios 100,000-foot solar airplane, and then a professor at Georgia Tech who runs the design center there, Dr. Alan Wilhite. All three of them did thought this was a dumb idea. Bert was open enough to say it before he started the study and didn't want to do it. At about the 48-hour point, they all kind of said, gee, this is kind of interesting. And at the end of it, they're like, this is better than sliced bread. And so we've been using that. Bert is very, very supportive of this, but you can see the comments about this. The combination of these numbers is radical. In the rocket industry, if you can get 5% more to orbit, they'll kill for that. And we're talking about basically doubling what you can do to orbit. So, to lead into the second half of the presentation, Red Jensen is going to talk about the third scale model glider that we've built and flown. This is a picture of us. This is a mini Sprite launch vehicle that Whitting Hill Aerospace has put together under a small business research contract. And this is a picture of the airplane in the first flight. There's a video that we're going to show at the end of the presentation that Red will narrate. But I bring this up only to point out that on the schedule right now, where we're at, this is fiscal year FY15, we've got two major activities. One is the flight test of the glider, and the second part is putting together the proposal to get the outside partner to make this into an X-plane program over the next 3 years, which culminates in 2 demo launches to orbit of that 100-pound payload. So with that, Red Jensen will step up and talk about the glider program. Assuming, where's Red at? There he is.
Good afternoon, my name is Red Jensen. I'm Chief Pilot for Class 1 and Class 2 SUAS aircraft at NASA Armstrong. I'm here today to talk to you a little bit about this glider in particular and about my job especially. I'm a lifelong modeler. I did model airplanes with my dad in the garage growing up. Taught me a lot about aerodynamics, airplanes, things like that, but what it really did was ignited a passion to want to learn more. And I ended up here at NASA, so that's kind of cool. I run the subscale research lab at Armstrong. That means all the aircraft 330 pounds or less come through my fingers, if you will. I'm responsible for the design, building, integration, and flight test of all these aircraft. So towed glider is one of many aircraft in the stable. Right now it's the big dog, though. It's kind of a cool project. In my prior life, I worked for a UAV company that built ISR platforms for the military. Traveled the world, got tired of that. I like being home. A little bit about the glider. It's a 1/3 scale Ventus 2AX. Bought it from Soaring USA a couple years ago here at the show. The outer wing panels and the fuselages are completely stock. The center wing and the center fuselage are custom built and designed in-house at NASA. It weighs about 62 pounds. It is powered by or guided by a Piccolo autopilot system, which is an industry standard autopilot. And we have a few other systems on board, differential GPS for enhanced navigation, ADS-B for position broadcasting so other aircraft can see where we're at. Even though we only fly in restricted airspace, we have the potential to integrate nicely with the rest of the world. And batteries, that's about it. Servos, all the normal stuff. We do have a data system on board where we record surface position. So anytime an elevator or rudder, aileron, flap, any of that moves, we record that actual position. And that allows us to build an aero model so we have a database for a flight sim so we can predict future performance. Here's a couple of pictures of the layup of the center wing. It's hollow molded construction, which is familiar to most modelers. Balsa wood core, carbon fiber skins, although it has an aluminum spar structure inside. The final weight of the vehicle is going to be somewhere around 300 pounds, and we're going to stress it to 6 Gs, so that's got to be a fairly substantial load. The outer wing panels that are currently on the aircraft are not adequate. They are being redesigned and rebuilt. Those off-the-shelf wings are great for the initial flight test, but it's not gonna work in the long run. So in there you can see the fiberglass structure and some of the skin. And on the right you can see the monocoque fuselage. The center fuselage weighs 7 pounds. I'm able to stand on it. It's a very strong structure. We buy all our stuff from CST, by the way. Here's another shot of the wing after it's closed up with some of the wiring inside. The yellow part you see there is a live skin hinge. It's a piece of Kevlar that actually flexes that creates the hinge. Again, model airplane technology, 100%. Nothing really earth-shattering there. It gets a little more complex when you start looking at the block diagram of the systems in the aircraft. Outside of the autopilot and the data acquisition system, it's a normal RC airplane. The one thing we do a little bit differently is we split up the aircraft into left and right half. So should we have a failure of a flight surface or a battery pack or something like that, we still can retain control. So there's a left half, then a right half, and they're all cross-wired. Again, nothing earth-shattering there. SmartFly power distribution boards, A123 batteries, SAVOX, and JR servos. Our tow aircraft is DROID, and DROID stands for Dryden Remotely Operated Integrated Drone. We are not Dryden anymore, we're Armstrong, so we've got to rethink that name. But we have 3 of these aircraft. They're basically a flying truck. We use them to test all kinds of technology, not necessarily the airplane, but the payloads that go inside them. This particular DROID, DROID 3, started out life as a Bruce Tharp Engineering Super Flying King, which is a double-sized trainer. Had a 100cc engine on it. We replaced that with a 170cc engine for more tow power. It's also got an alternator on board, makes its own power. Again, differential GPS and ADS-B on board as well. So we're only fuel limited with this particular aircraft. We can just refuel and go. We don't need to charge batteries or anything like that. The tow point is standard aero tow type thing. We tow from the trailing edge of the upper wing. We do have a release on the tow aircraft as well as the glider, and we also use a weak link. So in case something goes wrong, we've got 3 different ways that we can uncouple the mated pair and potentially avoid an issue. We've got time for some questions if you like, and then I'm going to show you a little video of sort of day in the life and some operations of the vehicle. Anybody have any questions at this point? All right, let's get into the video. Edwards Air Force Base, Rogers Dry Lake. Same place the X-1 broke the sound barrier, X-15, shuttle, all the cool stuff, you know. Best flying field in the world. 7 miles wide, 14 miles long, 300 days a year flyable. Good check. So that's Jim Murray hooking up the tow line there. He's one of our senior engineers, and we're just basically checking to make sure the release releases when it's supposed to. We have 3 methods to decouple should there emergency arise. We can obviously release from the glider, we can release from the tow line, from the towed aircraft as well, and we have a weak link in the system too, so you can simply pull hard and it'll break.
Thanks for coming.
And it breaks at about 1.5 times our max tow force, so max expected tow force.
6 flights today. First flight will be Jerry Solo.
We use 120 feet of tow line.
Checkout flight. Then we're gonna go through our ground checks, start up, and we're gonna get airborne as quickly.
And this is actually the very first flight of the vehicle.
It'll be relatively low altitude, 300, 400, 500 feet, something like that. We'll be taking off towards main base and circling again on this side. I will release probably right in front of us somewhere, and then simply circle down and land in this area again. We're likely to go higher later.
So the airplane flies real nice, no real squawks. It's kind of a big boat in the air, very easy to fly, no bad habits at all.
Airborne.
So we went to approximately 800 to 1,000 feet, first flight, and tow line will cut loose right about here. We fly at Edwards Air Force Base, Rogers Dry Lake. Same place the X-1 broke the sound barrier, X-15, shuttle, all the cool stuff, you know. And it's in free flight, and basically it's just a trim flight, functional flight tech.
We'll be ready to go here pretty quick. All right, we're ready to go, guys, whenever you are. Hey, Victor, we're going to do a test release.
The tow line there.
You ready? 3, 2, 1.
We're just basically checking to make sure the release releases.
Sorry, there's not much noise. It just makes a whooshing sound.
But this next pass here, I'm checking out the spoilers and the flap operations, looking for pitch changes, things like that. Very happy to report that there was very minimal pitch coupling. Lucky guess on my part with elevator compensation, but again, it just shows you that it's a kind of a sweet flying airplane. The other thing I like is this particular view right here. I think is a very attractive view of the airplane. If you're looking at it on the ground, sometimes it's difficult to sort of understand what it looks like being ground-based. It's tough to get a decent picture of it, but in the air, it's quite pretty, I think.
It's airborne.
So setting up for a landing here, you can see off to the right there, those black lines, those are one of the lakebed runways
Control's fairly sluggish,
that the
so
mini aircraft use. You can see what a wonderful flying field we've got there. You can land any direction, wind is usually not a problem. And that's about it.
Down one more.
So as you can see, as a modeler, I've kind of got a dream job. I get to do this every day, 100 to 1,000 feet, first flight.
There we go.
And tow line will cut loose right about here.
There you go, come on back. Now I'm going to overrun you, so I'm
And
released.
it's in free flight. And basically, it's
See, I
just a
was
trim flight,
overrunning
functional flight tech.
Okay. A little bit of right aileron trim, a little up elevator trim. Everything else nominal.
Sorry, there's not much noise. It just makes a whooshing sound. But this next pass here, I'm checking out the spoilers and the flap operations, looking for pitch changes, things like that. Very happy to report that there was very minimal pitch coupling. Lucky guess on my part with elevator compensation, but again, it just shows you that it's a kind of a sweet flying airplane. The other thing I like is this particular view right here.
No pitch change.
I think is a very attractive view of the airplane. If you're looking at it on the ground, sometimes it's difficult to sort of understand what it looks like being ground-based. It's tough to get a decent picture of it, but in the air, it's quite pretty, I think. So setting up for a landing here, you can see off to the right there, those black lines. Those are one of the lake bed runways that the mini aircraft use. You can see what a wonderful flying field we've got there. You can land any direction. Wind is usually not a problem. And that's about it. So as you can see, as a modeler, I've kind of got a dream job. I get to do this every day. Pretty cool stuff. So we hope to be carrying the shape, do some envelope expansion tests later in the year, and eventually get to the point where we're dropping the mini Sprite.
Any questions?
Red, and probably this is for Jerry. Jerry, yesterday we talked about, you know, the booster motor that you made out of the 3D printer that you used to, you know, you're able to restart it.
Oh yeah. So yeah.
But now, once that starts, is there any control on it? Can you shut it down as soon as you need to? Okay.
So the question is, yesterday in the presentation we had a question about the sustainer motor. Dr. Tony Whitmore, who is a retired NASA employee, is an instructor up at Utah State, and they have a PVC hybrid sustainer motor that we're going to use to propel the glider through that pull-up maneuver. We're actually going to fly this glider through that maneuver in the animation and release a small rocket. The sustainer motor that they're putting together are similar to the 3D printers that you see around the building. They're actually 3D printing or additive manufacturing the motor. The propellant is PVC and gaseous oxygen. Usually they use nitrous. Gaseous oxygen is actually better because there's no explosive on board. There's nothing. It's not a pyrotechnic. And so they 3D print these sections of it about 4 inches long, and they have a helical coil in it to increase the regression rate of the mass out the tailpipe of the motor, which increase the thrust. And it's because a straight tube, you only have so much area, but if you put it in a coil, it's like your intestines, you have a lot more surface area. And then they flow gaseous oxygen through it, and then to ignite it, they have 2 little electrodes. It's pretty much how you start your barbecue grill. You know, some of them it's a little clicker, some of them it's a little battery. It's exactly that. And so they flow the O2, throw a spark across these 2 electrodes, and off it goes. It's throttleable and restartable. So actually, if you go in the van on the tour that they'll probably be doing, the throttle that normally our research pilot would use when we were flying the DROID on the program that was briefed a couple years ago, that'll actually be direct throttle control of the rocket motor. As our test pilot, I got to mention his name, is Jim Less. His call sign is Clueless. He likes that. So he'll be pulling back on the stick for pitch control, increasing the throttle, the thrust of the rocket motor proportionally, just like he's flying a full-scale airplane. And so we're trying to make it as simple as we possibly can. Other question?
Red was flying the glider there, and he made it look easy, I guess. Are you going to develop more software and guidance system to automate the glider and monitor the tow and how the pair fly together?
So he's talking about tow force. Yeah, so we have a force balance on the glider that measures 6-axis, including tension, tow line dynamics. Eventually we're going to do the same thing on DROID, and we would like to autonomously tow the pair and take the pilot out of the loop eventually. So yes, we are absolutely looking into that.
Kind of along the same question, the tow line when you're towing this is quite a bit above the center of lift. Did you have problems with that in towing the plane, or did it tow easily?
No, it towed very easily. It's a little bit deceiving. There's quite a bit of weight in that center fuselage. Although I mentioned it weighs 7 pounds, that's empty. There's autopilot in there, there's batteries in there, there's payload release, there's all kinds of antennas and tow release. So the vertical CG on the aircraft is actually just above the bottom of that center fuselage. So the tow is actually going almost through the vertical CG. So it tows very nicely. It doesn't want to nose down at all. And since the glider has a higher lift-to-drag ratio than the tow plane, it naturally wants to tow higher. It trims out to a lower airspeed. It basically tows hands off. You just follow the tow plane around. It's very nice.
Oh, we got it.
So what are you doing about separation of the rocket?
Can't hear you at all.
Got it now?
Yeah, hold it right up to your mouth.
What are you doing about separation of the rocket motor from the glider before you ignite it? How far do you have to get it away, or are you doing a rail launch?
So on the model test that we're doing, we actually don't have to do anything. I mean, there's a safety review process that we follow in-house. For research experimental things in the model lab, they're more concerned that we don't hurt each other, although we really don't want to lose a test asset because that's cost and money and everything else. But if this were a piloted aircraft, or we're talking the 100, 150-foot glider, there's a full computational CFD analysis, separation analysis that you would do that takes into account the flow fields and Mach number and everything else that will be done before we do separate an actual booster. On the Pegasus, they did a 5-second drop-off of both the B-52 and the L-1011, and they gave them about 1,000-foot altitude separation. And that was because when they light off the motor, if it didn't work and it went bang, they needed that separation distance for blast radius. With an unpiloted glider, you really don't have to worry about that. You can take a lot more risk. So the thought was about a 3-second separation would get us the optimal performance. And interestingly, on General Pearson at the briefing I was at this weekend, or last week in Orlando, on the ASAT program, you might see a picture of it if you Google ASAT. They actually have an in-flight picture of the first pulse of the rocket motor lighting off on that at the 70-degree flight path angle, and it was a 3-second separation, and it's about 100 feet away from the F-15. But they did a lot of testing, and it was a proven rocket system before they did it.
What is your release altitude expected to be, and what is the zoom altitude expected to be before the rocket actually heads for space?
The release altitude for the concept is as high as you can get it, to be honest. Realistically, we're shooting for 40,000 feet to tow to that altitude. And then you release the glider. And actually, one of the nuances is that since we'll be out over the ocean most likely doing this, we've got a glide distance that's long enough to get back to land if you have an aborted launch.
Once again,
But to avoid that issue, one of the things that you can do, since the rocket motor, the sustainer motor, is start or throttleable, is you actually start it before you release the tow line and throw out a little bit of spoilers so you don't put slack into the tow line. Run a quick software check to make sure you have stable combustion on the sustainer motor. And then over the course of 5 seconds, then you can have it automatically release the tow line or shut off the sustainer motor and tow home if it doesn't light off. The pull-up maneuver, you'll gain another probably 2,000–3,000 feet during that pull-up before the release. So it'll be somewhere between 40,000 and 50,000 feet that the rocket motor's released at. Other questions? Thank you.